An important part of optics is going to be mirrors. So let's see how plane mirrors work. This is one that I actually have on my wall right here. But essentially, if you're standing over here, and this is your mirror, and you're a certain distance away from it, you're going to see your reflection over here, and it's just going to be looking like that. And what you could do is make a little equation that says that the distance from the object here is actually equal to, well, we're going to call it a negative distance from the image over here. And that's just because we have some strange notations. And well, if this is the positive distance, then it makes sense that this would be the negative distance. For concave mirrors, we can see how the mirror would be curving like this. But you can just imagine this guy being inside of a little cave here. Now let's try to label this so we can understand what's going on. We'll call this the object. And if that's the object, then we know that this is the front side of this mirror. And that's going to help us with notations later. But let's just remember that for mirrors, the fronts and the backs aren't ever going to change. So we'll just say that the front and the back of mirrors do not change. So that's going to be nice for later parts. Let's label some other parts. So we're going to see that this curving part of the mirror, we're going to call that the radius of curvature. And then we're going to call the point over here that's actually on the ground, we'll call it CR. We'll call that the center of curvature. And these can get some confusing sometimes. Usually this is labeled as an R, like a capital R for the radius of curvature, and usually this is just labeled as a C for the center of curvature. So those are those points. And then over here we have the middle is actually going to be called the vertex of the mirror. Convex mirrors are a little similar, but notice that the curvature is just backwards here. So we're going to call this thing the object again. We're going to call this the front again. And of course this is going to be still our radius, but our center would be way over here. This would be the CR at this point. So that's interesting. Now another cool thing is that for convex mirrors, we know that the images will actually always appear on this side over here. It will always be a negative DI for the convex mirrors. For the concave mirrors though, if you were to draw your little points, you would notice that this particular image would end up somewhere over here or something like that. So this is the difference between concave and convex mirrors so far. Another interesting thing to point out about these mirrors is the focal point. So I'll put that right here. That's going to be labeled as F. I'm going to leave the labeling on the concave mirror side because these are supposed to be positive CR, positive F. But for the convex mirrors, I'll put the points here, but I'm not going to label them because I don't want the signage to get confusing. These are going to be negatives and stuff, so we'll look at the sign conventions later. But let's just analyze this focal point right here. And for mirrors, what we can say is that only for mirrors, though, we'll take our center of curvature and we'll just basically divide that by 2. So 2F equals the center of curvature, and that's why we could find the F right in between there. This is only for mirrors, though. And so for a mirror focus, we also have one more equation that we can use to find it. 1 over F is going to be equal to 1 over distance to the object plus 1 over distance to the image. And so, well, this one's always going to be negative DI, so you always find the image on this side. This one may be positive or negative DI, so you got to be kind of careful with the signs, and we'll take a look at that in just a second. One thing about sign conventions is that you might find different signs in different places, so let's try to stay consistent with what signs we're going to use, and we'll start with the object distance. One thing we can note is that if we have a real object, we know the real object is always going to be plus DO, and this is always going to determine the front, so we'll start with that and we'll just claim that. However, you might end up where you find positive DO or negative DO somewhere in your calculations, but it's not a real object, it's actually an image. In that case, we'll call it a ghost. And so these are technically just images that can actually act as objects, but we'll call them plus DO, and if it's plus DO, it's still going to be in the front, and if it's minus DO, then we'll put it in the back. Height is also going to be a factor here, so let's look at the object height. We got an object right here. If it is a plus HO, that's height of the object, then it's going to be upright. If it is a minus HO, then you'll see it upside down over here. I'll put the image upside down just so we can sort of see what that would look like. It'll just be a little upside down guy right here. and we'll call that minus hi, that's the height of the image, which would be inverted. And then over here we'll call it plus hi, this would be an upright image, so you can see the differences there. Image distances are a little more interesting than the object distances. We'll start with the concave mirror, and we'll say that if we have a plus di, we'll put that in the front of the mirror, which would be over here, and then we'll call that a real image. And what that means is that we have light rays that are actually converging to a specific point, and they're going this way, so that way you can actually see the image. But if we have a negative di, we're going to put that in the back, and we're going to call that virtual. And what that means is that essentially you have your point that side, and the light rays are coming out this way. And so this is the difference sort of between a virtual image and a real image here. You can see this one on a screen because when it shows up on the screen here, oh, there's the image. This one does not show up on a screen because, well, the point was over here, so that's where you see the image. Now let's look at what the convex or plane mirrors would do, and these guys are always only going to give you a negative di. So that means that they're going to be in the back and they're going to be virtual, like this. So the convex mirror is going to be this one, it's always going to be in the back, this is a negative di, and over here it's always going to be in the back, it's a negative di. And let's just realize that if we have a negative di, that always means that it's a virtual image. So that always means this is a negative di. For the radius, remember we have the radius of curvature, which is just the curving part that's on the lens itself. But then we have the center of curvature, which is the point CR. Now the point CR for the concave mirror is going to be plus CR, and that's going to be referring to the front. So the concave mirror is this one, the CR is a plus CR. But for the convex mirror, that's going to be a negative CR, and that's going to be found in the back. So here's the convex mirror, and here's the point CR, but it's a negative CR, so that's why I didn't label these here. And that's going to be in the back. The focal length for mirrors are actually going to be the same sign as the center of curvature because of this equation here. So that just means that the concave have a plus F, and we're going to find that also in the front. And for the convex mirrors, that's just going to be the minus F, and we'll find that in the back. So the cool thing about mirrors is that they're relatively simple to work with. So far we've discussed reflection with all these mirrors, but now let's discuss magnification. And I'll write down this little formula here that says that M is equal to HI divided by HO, which is equal to negative DI over DO. And this is going to be the basic magnification formula that we can use for mirrors. Now I'm going to claim that if we have a plus M, then that's going to be an upright image. And if it's a minus M, then it's going to be an inverted image. So that would be referring to these things over here. And if we have an absolute value of M greater than 1, then this is going to be an enlarged image. And if we have an absolute value of M less than 1, then it's going to be reduced. Let's look at the magnification for a plane mirror. We know that since the images are always coming out negative DI, we're always going to have a virtual image. Now they also come out the same size and upright, and that's because M is going to equal 1. So when we see over here, if we get the same equal over here, obviously this is going to be a 1. But it's also a negative DI, which means this is going to be a positive on top, and so we just get 1 for that equation. For the concave mirror, it matters more where the object is placed, and we have a couple different scenarios here. If the object is placed past CR, this direction, then what's going to happen is you'll find a reduced image that is real and inverted. So that again just kind of comes from plugging in numbers into the magnification equation. And then if the object is at CR, which is on the point right there, you're going to find the object to be the same size. It's also going to be real and inverted. And that's because the M equals negative 1. If you put the object between CR and the focal point F, then you'll get an enlarged image that is real and inverted. If you put the object at the F point, something interesting will happen. You'll get no image. And that means that the object is technically invisible, or the image is invisible. And so di is going to be equal to infinity, or the image is gone, and m equals 0. Magnification is 0, you get no image. So same thing kind of would go up here. If m equals 0, you basically just get no image. M equals 0 means no image. And for between F and the mirror, if you put the object between F and the mirror right over here, then you'll get an enlarged image that is virtual and upright. And these are different scenarios for the concave mirrors. For the convex mirrors, we've already established that these will always be virtual because they're negative di, and we're also always going to get a smaller image. These will shrink things, and they will always be upright. So the magnification is always positive, but that means that you're going to get from 0 to m to 1 for the magnification here on the convex mirrors. The second part of this video is going to be about refraction, and so now we're going to need to start possibly including n's, that would be the indexes of refraction. In this particular situation, we're looking at a flat surface. Up here we have the air, here's the water, so we know the indexes of refraction of those things. Now our object is actually in the water here, so we're going to be able to call this side the front side because our object is always in the front over here. But what happens is we actually see the object kind of right here. So this is the image of that object. So our eyes see that right here. It's kind of weird. So we have to be able to calculate this by saying that the distance of the image, obviously from the top of the surface here, is going to be equal to negative n2 divided by n1 times the distance of the object. So this will be able to find you those distances there. Well, if we were going to identify what n2 and n1 were, let's just remember that n1 is always going to be in the front, and this is where the object is, whereas n2 is just going to be in the back. And so let's look over here. Since the object over here is in the front, we know n1 is actually the water, so that goes on the bottom here, whereas n2 is going to be the air, which is on top. Let's try refracting through a curved surface right here. We got a little fish bowl. The fish is in water, and since the fish is in the water, and that's the object, we're going to call it the front. So n1 is 4/3, and then here we're just kind of looking into that, and it's the curved surface, and we're outside in the air, so n equals 1. And we have this little equation here. We could say n1 over d object plus n2 over d of the image is going to be equal to n2 minus n1 divided by the CR, which is the center of curvature, and we'll put that right here. This is the point CR. This equation is for the center of curvature, but what about the focal length for a refracting surface? In order to do that, let's set the distance of the object equal to infinity. And if we do that, then what will happen is the di is the only thing that's going to be remaining. And if the only thing that's remaining is the di, because the object is way too far away. And you can see that di, well, that's where the focal point is, because that's where the image appears at the focal point. And so, therefore, di is going to suddenly be the focal point. So we've solved for f. And then we could also do that the other way around by setting the image distance equal to infinity. And the only thing you'll have left is going to be the do, and that is also going to be the f. So this is how you can actually solve for f for a refracting curved surface. Well, let's see how much space we have left for lenses, but we have to discuss the converging lens and the diverging lens. Now, the reason this is called a converging lens is because if you have your light rays coming in here, they're actually going to converge to a specific point over here on the right. And so they'll just kind of meet up right there. We'll call that converging. Whereas the diverging, if the light rays come through here, it's kind of going to act as if it came from this point right here, and it'll just branch off and just kind of go out in this weird direction here. That's what we call diverging. We've already sort of looked at that over here. And so from this conclusion, we can actually say that sometimes we might get a plus di or a minus di on this side. It could be on either side here, depending on where you put your object and stuff, you know. But over here on the diverging side, this is always going to be a negative di. So this is kind of similar to the convex mirror, where these are always negative di virtual images. And that just means that they do this type of stuff. It's important to get the signs correct for the lenses. So let's say if we were discussing this left side of the lens, we'll call that the radius of curvature. Remember, it's supposed to be the radius is referring to that curvature part. I'll call that R1 because look, the object would be on this side, so you know it's going to be the R1 side. But here's the thing, that curvature is really referring to a point that ends up somewhere over here somewhere. Now that blue point is the F point, the focal point, but I'll just say that CR1 in black over here is going to be referring to the center of curvature, and this thing is going to be on the right. So the center of curvature is on the right, or the radius of curvature is on the left for this particular situation. But if we come over here to this side, notice how now, well, this is still going to be R1 because our object would still be found on that side, but the R1 is on the left, and now the CR point, which is going to be somewhere over here, but CR2 is going to be now on the left side as well. So for this particular side, they're both on the same side, and here they're on opposite sides, and that's what makes things a little bit confusing. Now let's see if we could somehow calculate these F points from what we know. We can say that 1 over F is actually equal to 1 over distance of the object plus 1 over distance to the image. This is an important equation that will help us solve things. But we might also be given something like the index of refraction of some of these lenses. So you could actually take the n of that lens minus 1. This is for like a contact lens or something where you'd be looking at it through air. But you'd take 1 over CR1 minus 1 over CR2, and then you could actually take that. It's still equal to 1 over F for that particular lens. Remembering that CR1 would probably be this side and CR2 would be the other side, but you'd have to sort of figure out which side the object is on, and that will tell you which one's the R1 and the R2. Let's backtrack a little bit and head back to refraction. Okay, refraction or lenses. Now let's backtrack a little bit and discuss the image distance for refraction or lenses. So if we have a negative di, then we know that it's in the front and it's going to be virtual. But if we have a plus di, then it's going to be in the back, and that's going to be real. If we wanted to find the magnification for refraction, now we just simply have to add in the n terms. So let's say that n1 over the n2, and then we can multiply that by our negative di over the do, and that will help us for finding magnification for refraction. For the radius, that means the center of curvature for the refraction or lens, these particular points that we have here, it would be a negative CR for the front, but it would be a positive CR for the back. So in this particular case, since we find our CR point on this side, this is the back side, and so it would be a positive CR. And on this particular example, we would find our CR on the left side, and so here it would be that would be the front side, so it would be negative CR. Now let's take a look at the focal length for converging and diverging lenses. For the converging, it would always be plus F, and that's because the focal point appears on the back side, so referring back to the CR. And then for the diverging, it would be negative F, and that's because the focal points always appear in the front side. So just in case we needed to know that. Now let's discuss multiple lenses when you have maybe a mirror and a lens combination. Well, let's say you suddenly found an image. So you got your DI, and that would be the first image that you found. But now you're looking at the perspective of the next lens. And so you want to be calculating what the object would be for that new lens, because you have to calculate the object distance for the new lens. But it turns out that it's a it's a ghost object. It's just an image. So we're going to call this the ghost. We have a nice little equation we can use. The DO2, that would be the ghost, for that new lens is going to be equal to the distance between those two lenses minus this is the image that was formed from the previous lens. So if you apply this equation every single time you have the next lens in sequence, the next mirror in sequence, the next optical element in sequence, then this will always give you the correct signage for the DO2. And as long as you just double check, okay, for the DO, is it in the front or is it in the back? For these things, then you'll be able to figure out what's happening in your problem. So if you stick with this one, it'll work through the whole equations. Another interesting thing you can do with multiple lenses is stick them together like this, lens 1, lens 2, and that'll give you a larger focal length that'll just be somewhere over here. So you could take 1 over the sum of the focal lengths, and that'll just be equal to 1 over f1 plus 1 over f2, and etc. But just let's make sure that sometimes we have to account for the distance between those two lenses and then multiply their focal lengths down here. So this is just an additional term you might want to consider. But yeah, if you want to figure out what that sum of the f's would be right there, use that formula. We also have to consider the magnification for the lens mirror combos or the multiple lenses. So you would take the final magnification is just going to equal to magnification 1 times magnification 2 times magnification 3. You have to do it 3 times. So you just have to calculate these magnifications separately and then just multiply them together. Now let's say we want to set up a little telescope. We could start by looking over here, and then we'll set up a little eyepiece, and that will have a focus point that will converge somewhere over here. So we'll put that right there. But then we would also want to cross that with the next part, which is going to be the actual lens that we're looking at, because if you extend those two, then that focal length will be pointing here and the eyepiece will be here. So this is the eyepiece, this is the lens we're using, and if we have this set up, then we could use the magnification is going to be equal to the absolute value of the f of the lens divided by the f of the eye, and this will be for telescopes or for microscopes,